This video is sponsored by codingskill.net. Please visit our sponsor. Let's look at the quicksort algorithm. Quicksort is based on divide and conquer strategy. The worst case time complexity is O of n square. Best and average cases is given by O of n log n. Can be quicker than merge sort. Problem decomposition is hard. Combination stage is trivial or unnecessary. Decomposition transforms the input by using a partitioning scheme. Let's look at the problem decomposition step. We have this input list. We pick a pivot, in this case 4, and we create another list. The left side of the pivot are these three elements, and the right side of the pivot are these elements. This is the decompose step. We pick a pivot and we divide this into sublists. This section is less than or equal to pivot, and this right section elements are greater than the pivot, but they're still not sorted. So let's look at the recursion diagram. This is the input, and these are the elements in the list. Output is the sorted sequence of these elements for the given input. In the reduction step, we first pick a pivot. In this case, it's 4, and we select all the elements that are less than or equal to pivot and put them into a list, and another list where the elements are greater than the value of the pivot. So we have two subproblems, and these are two unsorted sublists. So if we sort the first sublist, we get these sorted 3 elements, and if we sort the second subproblem, we get these elements in sorted order. These are sorted. In the combine step, we have to concatenate for the pivot in between the sorted sublists. Let's look at the quicksort code. The method takes one parameter, the list that needs to be sorted. We first find the length of the list, and we check if the length of the list is less than or equal to 1. If so, it returns that list. This base case is same as the merge sort. Otherwise, we pick the pivot by finding the middle element. Middle element is chosen as pivot for performance reason. We then pass that array and the pivot to a method called get smaller than or equal to, and this method returns the left half of the list. All the elements will be less than or equal to the value of the pivot. We are going to assume this function is available to us. We then remove the pivot because we saw in the recursion diagram, we will put this in between the output of the subproblems. Then we call another method called get greater than, and we pass in the array and the pivot. This will return all the elements in the array that is greater than the value of the pivot. We will assume we already have this function. We then call the quicksort on v1 and concatenate pivot with the output of the quicksort of v2. So this directly maps from the recursion diagram. The result is in a new list. This requires twice as much space. This is called as out of place. Let's look at Inplace quicksort. This takes 3 parameters, the array to be sorted, lower and upper indices. If lower is less than upper, we find the index of the pivot by using a partition function. This is the recursive version of Horace's partitioning scheme. we will assume we have the logic for this partition already available to us. This carries out the decomposition of the problem. Then we make a recursive quicksort call that takes the array A, the lower index, and the pivot index -1, which results in the first section of the list. And then we call the quicksort on the second section of the list. Performance. Let's look at runtime cost analysis for the in-place quicksort. Base case occurs when pivot is located in the middle, and the time complexity is given by this equation. You can recognize this as the time complexity function for O of n log n. Worst case is when the pivot is located at the extreme, and this is the time complexity function for that case. And you can recognize this as a quadratic function. So we have O of n square as the time complexity. Sign up for your free coding interview coaching call. Sign up for your free coaching call by going to codinginterview.coach.